Thank you, and hello everyone. My name is Andy Katz. I'm a product manager at AWS, and I'm joined today by Tom Nightingale, who's a solution architect. Today we'll be talking to you about media processing workflows at high velocity and scale using orchestration and machine learning. Now, the motivation behind our talk is that viewer habits are accelerating and changing. Customers are expecting new content options available essentially anytime, anywhere, on any device with the best possible quality. What this means is over-the-top is growing rapidly, almost 10 times the pace of pay TV. In 5 years, this could be even a third of the market, up from 15% today. And there's this proliferation of choice, almost 400% more content choices per person compared to 2007 compared to 2017. And this is leading to fundamental changes in the industry. Viewer expectations are changing. Business requirements, this has operational implications. Unfortunately, AWS has solutions for providing viewers immediate access, providing them more content, and providing them more personalization. AWS Media Entertainment Solutions are built on a foundation of core services that include storage, compute, databases, networking, content delivery, orchestration, and machine learning services. And you have 3 different ways you can build your solutions, either natively, with partners, or custom. Let's talk about what each of those means. In a native solution, you'll spin up and combine multiple AWS native media services directly from the AWS console. This includes things like 5 elemental services that just recently launched at reInvent, or Amazon Rekognition for identifying scenes and objects and people in images and video, or ThinkBox Deadline for rendering on EC2 Spot instance fleets, Amazon CloudFront for delivery, or Kinesis Video Streams for ingesting that video, or Amazon Poly for converting text to speech. You could also leverage AWS's rich ecosystem of partners that enable hardware, software, and service solutions in a range of cloud-enabled media workflow solutions. Finally, you can build custom solutions out of AWS's core services, which provide you true primitives on which to build modular custom solutions to fit your needs. Now, the AWS stack for media streaming workflows has a wide range of options. There are many services for ingestion and creation. There are services for storage, for processing of your content, and delivery of your content. Today, we're going to focus on 6. Elemental Media Convert, Amazon Rekognition, AWS Step Functions, Amazon Comprehend, Amazon Translate, and Amazon Transcribe. We'll start with orchestration, which is AWS Step Functions. And we'll say, when you think about your media supply chain, your digital asset management, do you recognize yourself in this? You have tasks in your supply chain where you may want to sequence them in order, do A, then B. If A fails, you may want to retry that task. You may want to set up try, catch, finally patterns for those tasks. So keep trying, but if all else fails, go somewhere else and do a cleanup. You may want to select what task happens after step A, depending on what step A's outcome was. So for example, if A is positive, do B. If A is negative, do C. And finally, you may want to run things in parallel for higher throughput and then go on to the step that follows. If you recognize yourself in any of those workflows, you may want to use AWS Step Functions. It's a hosted workflow orchestration service that makes it easy to coordinate components of distributed applications using visual workflows. So for example, suppose you have a digital asset management workflow where you're ingesting a series of photographs. You have a picture, you want to identify what's in the picture, and at the same time you want to transform that picture into other formats, like for example, a thumbnail. The workflow I've just described you see on the left, what you see on the right is a state machine that does that just for you. It has a variety of states. These are shown in green here. There's tasks, there are choices that give you conditional logic, there are fail states when you have a terminal condition, and there are parallel states where you can do things in parallel for more efficiency. So in this case, you see the first task is to extract image metadata. Next, if it's a file type that's supported, yes, it goes down the left branch. If not, it fails with the workflow. When it is the right file type, you can store that image metadata in a database such as DynamoDB. And then in parallel, you can make a thumbnail with a Lambda function and call Amazon Rekognition to identify what's in the picture, in this case, mountains, people, and snow, and add those tags to the Dynamo database that also knows where the original file is located and where your thumbnail is located on S3. How do you make this? In Step Function, you configure your workflows as a declarative JSON document. So that same workflow we just looked at is described in JSON on the left here. It has a place where you start. In this case, you say start at the first state, which is extract the image metadata. You have a list of states. Each state has a type, It has a resource, it has input and output filtering of its metadata, and you can also have catch and retry handling in that task state. And you build up your workflow as a series of blocks of JSON like this. And Step Functions takes that and generates the graph like you see on the right. This is an image of the console of that same workflow being generated from the JSON, which allows you to monitor your executions as they run and after they complete. So when you think about media workflow management using AWS Step Functions, it gives you an opportunity to streamline, orchestrate, and optimize your workflows. You can increase your productivity by coordinating end-to-end workflows that reduce the time to design, test, deliver, and iterate, really optimize your use of your resources and your talent. It increases your agility. You're able to make decisions about these workflows in real time and gain real-time visibility into workflow progress of long-running workflows. Workflows on Step Functions last seconds up to a year. You can easily adjust your workflows as your needs change. So when you need new media sources or new destinations, you can make changes quickly. This allows you to create new workflows and new distribution channels faster for less effort and money. And finally, it's resilient. It lets you handle variations in the volume of incoming content. So it scales for you automatically. You increase production capacity on demand and proactively address any bottlenecks. File-based transcoding, which is re-encoding and converting from one file format to another, often change the bit rate or the resolution or other properties of the file. Now in AWS, you have many media processing options. The newest, of course, is AWS Elemental, which gives you on-prem and cloud solutions for both live content, video on demand, and just-in-time with professional-grade output. There's also Elastic Amazon Transcoder, which lets you have fast integration with prosumer content. AWS Marketplace offers a number of AMIs with licensed software for minimal disruption in your workflows. And then finally, you can build it yourself through self-contained custom solutions. We'll look at some custom solutions first. So one custom solution was built by a customer called Frame.io. Frame provides customers the ability to collaboratively edit their video. And one of the challenges they had was they needed a way to flexibly coordinate video transcoding between videos that were small enough to process by a Lambda function and videos that were big enough where it made more sense to process on an ECS container. And so this is an example of a workflow that's part of their overall workflow that decides what compute resource to use for the job. So it starts at the top with an encoder decider, which looks at the file and says, is it small enough that I can encode it on a Lambda function? And if so, go down the left branch. And if it's larger, run the ECS encoder by calling ECS to run task, wait, check the status, and if the task is not done, wait a little more and check again. And essentially by this polling loop, find out when the job completes and exit successfully or unsuccessfully depending on the output of the transcoding job. This improved the performance of their workflow, lowered their costs. They found this code is easier to manage and debug than doing it with a series of queues and coordination, and it increased the velocity of their code releases 20-fold. Another example of a custom solution is Thomson Reuters. Thomson Reuters processes a lot of videos. They typically need to transcode 350 news video clips every day into 14 different formats as quickly as possible because news has to be fresh. And they do this with FFmpeg transcoding, which means the processing time is almost commensurate with the length of the video. And FFmpeg is a sequential process, so if you do it in series, you're going to wait a long time for all that video to process. So the solution was to use step functions to split the video into chunks using step functions Lambda and S3 to process things in parallel. And so what you see here on the left is that video workflow, which prepares the split, performs the split, prepares parallel processing of all those 3-second chunks, and then reassembles the segments into a final output. The benefits is they now have parallel processing. They've reduced the processing time from 20 minutes down to 2 minutes. And of course, the bigger the source video, the more segments they make, and the bigger the time savings. What their solution architecture looks like is something like this. They have a step function state machine that's coordinating a series of Lambda functions. The source video on a S3 bucket, they identify the keyframes. They use those keyframes to chunk the video, put it into a second bucket, which they then can trigger Lambda functions from that S3 bucket to process all those segments, put into a destination bucket, where the state machine follows that process segment bucket until it's full, at which point it then runs a final Lambda function that concatenates all those segments back into the completed output video. It's a very clever way to do things in parallel, fanning out with step functions. And here's another way, using AWS Elemental Media Convert. MediaConvert is a file-based file processing service that lets anyone with any size content library easily and reliably transcode their content on demand for broadcast or multi-screen delivery. This gives everyone access to professional-grade video features and quality. There is no software or hardware to manage. It's a fully hosted service. It automatically scales in response to variations in the incoming volume, and which gives you the ability to manage capacity and control over the order in which jobs are completed. The basics are: primary unit of work is a job that specifies input and output. You can have output presets to create a single output. You can create job templates for commonly used job settings, particularly useful when you're doing fixed sets of outputs on a regular basis. And you use a queue. All jobs are submitted to queue. Queues let you separate groups of jobs for processing at different priorities, and they're all processed in parallel by MediaConvert. And so it's good for almost anyone with video content that needs to convert it for delivery to a consumer device. This can be companies with content distribution workflows for premium video or short-form web content. It can be customers that are processing video content in the cloud today or planning to move video content to the cloud. Companies with high volumes or varying volumes can both be supported by MediaConvert because it is a pay-as-you-go service. Essentially, any video provider enterprise wanting to streamline their transcoding operations could benefit from taking a look at MediaConvert. Now, with MediaConvert, you can build even serverless solutions. And for a powerful and customizable solution, I'm going to have Tom tell you about an AWS Answers video on demand solution built with MediaConvert and step functions.
Thanks, Andy, and hello, everybody. My name is Tom Nightingale. I am a solutions architect with AWS. And for this section, I'm going to be talking about our video on demand solution. Just before I get to that, I wanted to introduce everybody to AWS Answers. This is a site where you'll find all the solutions that my team build. What is a solution? A solution is more than a demo, more than a POC. These are production-ready or near to production-ready reference architectures that you can spin up in your account within a couple of minutes, and you'll find solutions for a broad range of subject areas and industry verticals. Each solution comes with its own landing page where there's a brief on what the solution is trying to achieve. There is an architectural diagram to give you some idea of what it is that we're building out, an implementation guide which gives you step-by-step instructions on how to deploy the solution, and some further reading on the actual details of the solution itself. We also have a CloudFormation template for each solution so that you can spin it up in your account within a couple of minutes. And finally, code for each solution can be found linked on this site and isn't stored on AWS Labs on GitHub. So lots and lots of good content on this site, and I highly recommend people to go and take a look through all the subject areas. So the video on demand solution is a reference architecture that demonstrates how to build out a serverless end-to-end workflow for processing video content on the AWS cloud. This is the sort of overview of the architecture that we're using. The key components for the workflow are AWS Step Functions and AWS Elemental Media Convert. We have a number of other services that we're using for the solution as well. S3 for storing our source and destination content, and we have Amazon CloudFront fronting our S3 bucket for HLS and Dash content so that we can deliver that content globally. The step functions are all backed by AWS Lambda, and then we have CloudWatch for monitoring the Elemental Media Convert, Amazon SNS for sending out notifications to the administrator, and then we're capturing all of the information coming in and out of the workflow in Amazon DynamoDB. So the idea is that we are dropping a single source file into that S3 bucket that triggers our workflow. We're going through a series of steps to ingest and process that file. We're sending an encoding job to Elemental Media Convert, and then once that job's completed, we're running a final step functions publishing process where we're just gathering all the information about our outputs and writing that information to Dynamo and sending out an SNS notification to the administrator. So there's a couple of sections that I want to focus on. The first thing we're going to do is look at the actual workflow itself and specifically the step functions. Just a note on the solution overall, when we first tried to build out this solution, we looked at what customers were doing in the real world. We talked to a number of different customers about what their requirements are, and it became very clear early on that there were many similar themes to what people were doing with video on demand, but actually each customer had very specific requirements. So we knew at the very start that we weren't going to be able to build a one solution fits all for all of our customers. But what we have got here is something that demonstrates how you can use AWS architecture to build out these workflows. And then we have some steps here that you can see on this slide, which is more really a sort of a demonstration about how the types of things that you would do. So with step functions, what we've done is we've broken down the workflow into nice small steps. We've taken very much a kind of microservice approach to the workflow. And the intent there is that each of these steps can be easily modified, changed out, swapped out. You could expand on this architecture to build out much more complex workflows depending on what your requirements are. So for this version, for this demonstration piece, what we have here is a source file being dropped into S3. That triggers our ingest process where we're just validating that content. We're running media info on that source file, which is an open source software that will extract metadata about that video file. Once we have that information, we're taking that and writing that out to our Dynamo table, and then we're sending out a simple SNS notification just to say that the workflow has started. When we get to the processing stage, we have a profiler step. This is a Lambda function that then reads in that metadata that we gathered from media info. It looks at the height and the width of the source video, and based on that, it sets an encoding profile. Our encoding step then sends that builds out a encoding job based on that profile and sends that to MediaConvert. Again, we're writing out all the information gathered through that process out to our Dynamo table. MediaConvert does our transcoding and creates the outputs, and once that completes, we're triggering our publish step functions, and this is just the last steps where we're gathering the information that's come out of MediaConvert, checking that we can get to those assets in S3 and they are where we think they are, and then writing out a final the final bit of information out to Dynamo about the workflow, and then sending a publish notification with the links to CloudFront distributions and just a summary of the events. So nice and simple, broken down into sort of simple steps and a kind of microservice approach so that you can easily customize this. And then one final thing I'd note on here is, as I mentioned, we're updating Dynamo throughout each of these different workflows. These Dynamo steps are actually the same Lambda function that we're calling each time. So one of the benefits to this approach and to using AWS step functions is now we have reusable code. We have a single Lambda function that takes an input, writes it out to Dynamo, and we can actually drop this anywhere into the workflow whenever we need it. So a nice, powerful way of creating workflows using step functions. Next section, let's take a slightly closer look at the actual encoding process. One of the great things about the MediaConvert service is how flexible it is and how easy it is to get set up and running. You actually only really need one thing to get going with MediaConvert, and that is the API endpoint for your account. So within every account, within every region, there is a custom API endpoint that you can hit. And once you have that, you're up and ready to go. There's very little pre-requirements for setting up MediaConvert. If you want to go in and create your own output presets and things like that, create queues, you can. But just to get up and running, you really can just start submitting jobs to that API endpoint, and you're good to go. So this on the left here is a snippet of the Lambda function that creates the job. the two things to highlight is, again, there's that endpoint that I mentioned just a second ago. Once we have that, we can submit jobs to Media Convert. And the other thing to note about the solution is we're actually using the user metadata that's part of the JSON object that you pass to Media Convert. You can actually add in your own custom metadata. And as part of the solution, we're using that to tag all of the jobs that are being submitted to Media Convert with the GUID, which is the unique identifier for all the assets as part of this workflow, and then the workflow name or ID, so that once Media Convert completes, it sends a CloudWatch event. We get a CloudWatch event which we can monitor with a CloudWatch event rule, and the CloudWatch event rule is actually looking for any statuses of complete, but it's also filtering those outputs with that workflow ID or workflow name, and then that way we can then trigger our final step functions, publishing step functions, directly using that CloudWatch event rule, but we're only triggering it for assets that have been sent to Media Convert by this workflow. So again, a nice way to interact between step functions and Media Convert. The last piece I wanted to just touch on with the solution is error handling. We built a simple error handler, which is a Lambda function that is connected to both the CloudWatch events. So if there is an error message that comes out of Media Convert, it gets triggered. We also have a simple error library that's added to all the Lambda functions that make up the step functions workflows. And either of those, if there is an error, it will call our Lambda function, passing it the event data, so the information that came into the Lambda function, and then the actual specific error message itself. And then that Lambda function writes that information out to our Dynamo table and sends out an SNS notification to the administrator, say something's gone wrong and here are the details. And the nice thing about adding this is, as part of the workflow, we were capturing state in the Dynamo table. So we have state for ingest, processing, encoding, and complete. And then this adds in error as well. So if you could imagine, if you run through hundreds of videos through this workflow, you'd be able to query the Dynamo database and get an overview of how many files have been completed, how many are in the encoding stage, and if there were any errors and which files failed. And that is as far as I'm going to go in terms of the details of the solution today. Hopefully that gave you some insight into what we've tried to build here. As I mentioned, you'll find the solution on AWS Answers, and the source code for the solution is also available on AWS Labs. And with that, I will hand you back to Andy.
Well, thanks, Tom. So besides having transcoding solutions for digital asset management in the media supply chain, we're also introducing machine learning analytics to enable you to gain actionable insights from your content, both from your customer interests, managing your infrastructure, monetizing your content. So how do we go further? We go further by allowing you to add intelligence to your media workflows, whether you're ingesting, storing, analyzing, or delivering. Machine learning can be applied across the media value chain, from content creation and post-production all the way to publishing and distribution. This can be tasks such as tagging on ingest, or detecting celebrities, or auto-categorization of your content, all the way at the end to ad personalization, translation services, or demographic and sentiment analysis of the feedback you get from your customers. Now within AWS, we've been focusing on bringing that knowledge and capacity to our customers, and in doing so, we see the machine learning stack as having three key layers: frameworks and interfaces for machine learning practitioners, platform services that make it easy for any developer to get started and get deep with machine learning, and application services that enable developers to plug in pre-built AI functionality into their apps without having to worry about the machine learning models that power those services. The bottom layer is really for expert machine learning practitioners. These are people comfortable building deep learning models, working with deep learning frameworks, building clusters. They can get extremely deep. Now, everybody's got a solution for ML platforms, which we think of as the middle of the stack, but none of them have been easy enough for everyday developers. And if you think about it, when you're trying to build a machine learning model, it's not easy. There are a lot of blockers every step of the way. And so that's why at the top layer of the stack, we serve developers and companies who want to add solution-oriented intelligence to their applications through an API call rather than developing and training their own models. So we'll look at some of these. First, we'll take a look at Amazon Rekognition. Amazon Rekognition is a deep learning-based image and video analysis tool. For those of you that use Rekognition, you know there's a variety of options for processing media content. So whether you're taking video clips, extracting frames, and then sending those to Rekognition, the vast majority of content is image-based, but some content is also media-based, it's video, in which case there's different needs. So when you're thinking about images, you may look at facial recognition or facial analysis or identify celebrity. But when you're looking with video, there's other things you might need, like object, scene, and activity recognition or person tracking. Amazon Rekognition makes it easy to add video and image analysis to your applications. You just provide an image or video to the Rekognition API, and the service can identify the objects, people, text, scenes, and activities, as well as detect any inappropriate content. Amazon Rekognition is also providing accurate facial analysis and facial recognition even with live streaming video. So you can detect, analyze, and compare faces for a wide variety of user verification, cataloging, people counting, and public safety uses. So we'll talk about incorporating this into your media intelligence pipeline. And we'll simplify by thinking about 3 stages of that pipeline. Ingesting petabytes of images or mixed media assets, using Rekognition to enrich the metadata about those assets, and then use that to enhance the search experience for those assets over time. So our use case is going to come from a well-known magazine that highlights articles about science, geography, history, and world culture. The magazine also permits users to contribute photos through a mobile app. And one thing you can be sure of is that year over year, there'll always be more and more photos being uploaded and contributed to the archives. And as they migrated petabytes of images into AWS, they asked themselves, how can we enrich the metadata as we do this in AWS? So let's take a look at that. One of the system requirements was to create a unique ID for global registration of all these images. They need to identify assets, so naming convention method, especially if we're going to run this in a distributed fashion across multiple businesses or even just within the company itself, a naming convention just doesn't scale. So when you have multiple versions of an asset, maybe their name is the same, and we need a way not only to register these globally, register these assets they pass through the system, they can understand if they've been recognized or not, but also be able to see down to the bit level in the actual images itself and not rely anything else as a benefit of that is inherently handling these parent-child relationships, the content. So as you maybe have an app that has a master asset, you have multiple file types underneath that you've created, perhaps through transcoding, that you can know all can be categorized and registered under a single system. So what are the key components of this asset ingest and registration? On the left, you can see the 8 key components that include step functions and Lambda, as well as Rekognition. And on the right, you see the key Rekognition API endpoints that are used in the application itself. So it's actually a lot of the heavy lifting here is done by step functions, Lambda, and Rekognition. And this is the solution architecture for this workflow. You can see the steps that are ingest are in blue, the steps that are processing are in orange, and the steps that are the delivery of the content are in green, and how they relate to each other. For example, S3 is used for when images land in the archive. S3 is part of the ingest process where Lambda watches for an S3 put that kicks off a step functions workflow. And the goal is that as we get the asset in S3, you want to immediately get it into a step functions workflow so that we know the chain of custody is maintained and it is being taken care of in a safe place all the way through the workflow. So what are step functions doing? First, Lambda is a natural fit for image processing with Rekognition. It can detect when an image or a video goes into the bucket and call Rekognition. The caveat is it's inherently stateless. And in a workflow, processing pipelines are multi-stage, and each stage represents a change in state. So step function-based state machines are an absolute must in order to ensure processing at high velocity and high scale. What you see in this workflow is a series of steps that checks, does the ingested image have a UUID? If it doesn't, get one. If it does, check if Rekognition has processed the image. If it has, then check the size of the image and whether or not it's to be resized. If it needs to be resized, do so, and then present it to Rekognition, and then save it in Elasticsearch DynamoDB for use for people downstream that want to find those files in the future. And again, this is a workflow that's run for every single image that's brought into the bucket, regardless of its point of origin. So some example responses from Rekognition. You give it an image of a hawkbill sea turtle. It gives you a set of labels with varying confidences that it's a reptile, it's sea life, it's a sea turtle, it's a tortoise. Or on the right, you get a mountain gorilla, and it identifies that it's an animal, a gorilla, a mammal, possibly a monkey. And the idea is that independent of the composition of the photograph, it's able to identify things important for tagging. These JSON labels are well suited for unstructured data in Elasticsearch or NoSQL databases like DynamoDB. Multiple labels can be used to effectively widen your search results, and the minimum confidence threshold helps you remove false positives from your data set, and minimum labels or max labels help you limit the return results. Client-side filtering can also be used to rank results by that confidence score. So that's why you get rich parameters, rich tagging on your images. And finally, what does the user experience look like in the end? The user experience is straightforward as I put in what I'm looking for, it finds an image, it gives me the confidence scores. The increasing maturity and growing availability of machine learning algorithms and artificial intelligence services have unlocked new frontiers in analytics across several forms of media. Through the use of AI tools and services, it's now possible to extract valuable metadata from pictures, video, and audio files in order to inform and enable a variety of use cases, such as object detection, facial recognition, content moderation, text extraction, transcription, and translation. AWS is offering many such AI services that enable customers to build simple, intelligent applications. We talked already about Amazon Rekognition. Talk a bit more in a moment about two more. Amazon Transcribe, an automatic speech recognition service that makes it easy for developers to add speech-to-text capability to their applications, and Amazon Comprehend, which is a natural language processing service that makes it easy to identify the language of text, extracts key phrases, places, people, brands, or events, understands how positive or negative the text is, and automatically organizes a collection of text files by topic. By combining these machine learning analytic services with Amazon's managed data storage and database services, you can easily build highly available and scalable applications that address a wide variety of real-world use cases, such as immediate response for public safety and security, providing a searchable library of videos and images, sentiment analysis for advertisers, retailers, or social media analysts, customer analytics, and localizing web content for international users. So we take a look at the Amazon machine learning stack again. Again, we talked about Rekognition. So now we'll take a look at examples that make use of Transcribe and Comprehend. One of the things that's interesting is there's so much data now that's being locked up in audio and video files. And the problem is that it's really hard to search audio well. So the best way to do it is actually to convert audio to text. And traditionally, how people have done this is they've hired manual transcription agencies. They're expensive and they're time consuming. And so typically people only pick out the most important things they want to transcribe and they leave the rest behind. All this data and all this value is sitting out there and it's not being taken advantage of. Amazon Transcribe solves this problem. Transcribe does long-form automatic speech recognition. It can analyze any WAV or MP3 audio file and return text. And it's super useful for all kinds of things like call logs as substitutes for videos or capturing what's said in a presentation or meeting. Another new service is Amazon Comprehend, which lets you discover insights and relationships in text. Comprehend can understand documents, social networking posts, and really any other data in AWS. You simply provide the data that you're storing in your data lake in S3 via the Comprehend API. Then Comprehend uses natural language processing to give you highly accurate information about what it contains in 4 categories. Entities, which are really people and places and dates and brands and quantities. Key phrases that add significance to the language. What language is being used. And sentiment, whether or not people are feeling positively or negatively about that content. So now I'll put these together in a new AWS Answers solution that's coming up, Media Analytics solution. This is a proposed architecture we're working on that details a method for extracting important metadata from audio, video, and image files. When content is put to an Amazon 3 bucket from a variety of sources shown on the left, it'll trigger an AWS Lambda function that will start a step function state machine that will analyze the media using these native AI services. Each Amazon AI service, recognition, transcribe, comprehend, will extract important details from the file. And then Lambda functions will store the full metadata and transcript in an S3 bucket as a JSON object. And high-level metadata as well as the links to the full metadata file will be indexed in an Amazon DynamoDB table and an Amazon Elasticsearch cluster. So in a series of steps, first users use a simple website to upload text, image, video, or audio files from their local machines. These files are assigned a UUID and put in an S3 bucket where it's encrypted. That bucket invokes an AWS Lambda function that will start a step functions process, step function state machine shown in step 4. That state machine will simultaneously invoke 3 parallel processes, one for video, one for audio, and one for image files. And depending on the file type, different AI ML services will be invoked. If the file is an image, say PNG or JPEG suffix, the state machine will invoke 3 parallel image recognition processes using Amazon Rekognition. Amazon Rekognition will respond with metadata for labels, celebrities, and faces detected in the image, and the raw results will be stored in S3. The resulting S3 key as well as an array of labels, celebrities, and facial features will be passed as input for the next stage of the state machine. On the other hand, if the file has a video, as shown in step 6, i.e. a MOV suffix, the state machine will invoke 4 parallel video recognition processes using Amazon Rekognition. The state machine will also use the job status polar patterns to regularly check for the job status to know when recognition completes the task. And when the recognition job completes, the resulting labels, celebrity, facial features, and person tracking metadata is retrieved in the same way. The raw results are put in S3. The resulting S3 key, as well as arrays of labels, celebrities, and facial features, will be passed as input for, again, the next stage of the state machine. And finally, if the file is an audio file, it's an MP3 or a FLAC or a WAV suffix, then the state machine will also invoke an audio transcription process using Amazon Transcribe. The state machine will then use the job status polar pattern again to regularly check the job status of the transcription. And once that transcription job is complete, the raw transcript will be retrieved from Transcribe and stored in S3. And again, that S3 key will be passed as input for the next stage of the state machine. Once that's complete, you get to step 8. When the transcription process is complete, it will invoke a natural language processing using Comprehend. The state machine will invoke 2 parallel processes to take key entities and phrases in the transcript. Comprehend will respond with metadata, and the results again will be stored in S3. The resulting S3 key, as well as arrays of key phrases and entities, will be passed as input for the final stage of the state machine, or the next stage of the state machine. Step 9. If the file can be analyzed for both video and audio, the state machine will actually invoke video recognition and audio transcription processes in parallel. And the final stage, step 10, the state machine stores all the results in a DynamoDB table. Each item contains basic information about the file, size, bucket, key, etc., arrays of metadata provided by the ML Analytics services, as well as links to the raw results stored in S3. Upon putting the data in Dynamo, Dynamo invokes another Lambda function that indexes the media file metadata in an Amazon Elasticsearch cluster to make it easy to search and find. And then users can now search for this data using an API that's hosted on API Gateway, shown here in step 12, and use the Lambda function to execute that search. Again, this will be available soon in AWS Answers. Now, taking a look, what's the state machine look like behind the scenes? This is the state machine doing the work, and what you can see is 3 parallel paths. If it's an image, it goes down to the group on the right. In this case, it's not an image, so it doesn't execute that. But it is a video, has audio and video in this case, so it goes down the middle branch, which asks, is it audio? If so, extracts the audio using Transcribe, and then Comprehend. And if it's a video, then you see on the right, it goes through and uses recognition for those 4 parameters we mentioned, the video label, the video celebrity identification, the face parameters, and the person parameters. And when all is done, it brings it together at the end and writes it in Dynamo and exits the state machine. Now, putting it all together, there are lots of applications of machine learning across media entertainment segments. Acquisition, visual effects and editing, digital supply chain, digital asset management, publishing, playout and distribution, over-the-top, and analytics. And AWS has solutions for all these areas. We can help you at each step of the video chain. We can help you build your way, whether you want to use native AWS solutions, work with AWS Partner Network, or build custom solutions. What this means for media technologies is from end to end, AWS enables you to build faster, smarter, and more efficiently. Thank you, and we'll take a few questions.